Okay, everybody, welcome to class. Happy Halloween. Okay, we will get started today. Let me talk about our learning objectives, and then we're going to finish the question that we didn't get to last time. So our learning objectives today is we're going to learn about one of these classic equations in material science and mechanical engineering called the Hall-Petch equation. It relates the yield strength to the grain size. The grain size is something that we can change in materials, and so it's important to know what that's going to do to the strength, and Hall-Petch is how we do that. We're then going to talk about, what's the trade-off between ductility and hardness and strength, right? And how can we change those things as we process materials? We'll talk about grain growth. We're going to describe different mechanisms of deformations, including some for ceramics, polymers, and glasses, and other materials. We'll get to viscosity, and we'll have a few more comments on how molecular weight, crystallinity, deformation, all can change the mechanical properties of polymers. So let's pick up where we left off last time, which was this question. So I'm going to start this one. The question said the following. It said, determine the tensile stress that would be applied along the 110 axis of a silver single crystal that will cause slip on the 111 plane in the 011 direction, right? So that's the slip system, is the 111 plane in the 011 direction. And it tells us that the critical resolved shear stress is 6 megapascals. So just to remind you of what these problems do, when you apply a stress normal to the face, you don't think there's any shear stress, but as it turns out, there's some plane that's tilted, and on that plane, there's a component that's a normal stress, and there's a component in that plane that is a shear stress. So when the shear stress goes above what we call the critical resolved shear stress, then you get slip. Atoms start sliding past each other. So if the resolved shear stress goes greater than 6 megapascals in that 011 direction, then we're going to get slip. So all we need to do is we need to calculate what is the resolved shear stress in the 011 direction when you've got that plane and you've got the loading direction, right? So our loading direction, we determined last time, the problem states really, that it's right there. We know that it's the 111 plane, therefore the normal to that plane is also the 111. We remember that that only works in a cubic crystal system. That does not work in tetragonal, orthorhombic, hexagonal, anything else, right? Which is why I will only give a cubic crystal if it's on a test, right? And then the only thing we need to do to solve this, the equation is pretty straightforward. The equation for resolved shear stress, tau, right, it's going to be equal to the stress that you apply multiplied by cosine of phi times cosine of lambda. Where lambda and phi are the angles between your loading direction and the normal, and between your loading direction and the slip direction. That's phi and lambda. And we worked out phi together, and we remember that the way to do that is with the dot product, right? You take the dot product along the top, you divide that by the length of the two vectors, and that will give you the angle between those vectors. So in the next couple minutes, go ahead and work out what the cosine of lambda would be, and then plug it into this shear stress equation, and figure out what would be the applied stress necessary to get slip in the 011 direction. Anybody need help? What's up?
Is it for the lambda, the dot product between 111 and 011?
Nope, it's going to be between 110, that's the loading direction, and the slip direction 011. So, for lambda, yeah. So 110 and 011. What's up, Bryce? Yeah. That good? A little more? Questions? What's up?
I'm trying to figure out what I'm dot product.
Okay, so if you want lambda, that's the angle on the right, then it's between the two vectors 110 and 011.
Okay, that makes sense.
Yep. Yep. Okay, maybe two more minutes. Let's wrap this one up. It's pretty straightforward calculation.
Can't plug them in down.
How does it normally work? You normally have a keyboard pop up or what?
Yeah.
Oh, it says it's paused. But we're not paused. Here, let me try this real quick. Let me pause and then restart. No, it's working? Okay, hey, if that ever happens, let me know and I'll do a quick restart like that. Okay, we're going to wrap this up. Okay, let's see what the answers were. So lots and lots of answers. A big chunk coming in at 14.7. I think that's the right answer. Let's work it out together. Okay? So we did one example of a dot product before. On this one, the dot product is between the angles 0, 1, 1 and 1, 1, 0. Right? Those are the two angles between our loading direction and our slip direction. So the dot product is going to be easy. It's going to be a 0 term times 1, a 1 times 1, and a 1 times 0. So that's just 1 in the numerator. Then in the denominator, we've got 1 squared plus 1 squared, and we've got 1 squared plus 1 squared. So this is going to be root 2 on the bottom. Root 2 times root 2 is just 2. Half? Math? Somebody? Just math? 2? Alrighty. Alright, we plug that in. So we know that for the critical resolved shear stress, that needs to be 6 megapascals. We've got 2 over root 6 and 1/2. Let's solve for sigma. Is 14.6969. Yeah, so it's 14.7, okay? So that's what most people entered onto here. Any questions on this? 14.7 megapascals. Any questions on slip in single crystals? Pretty straightforward. The key thing is to remember how to do this dot product to get that angle, to make sure that you choose the right angles, right? When I say this, that it's applied along the 110 axis, causes slip along that, can you interpret that and figure out which things you need to take angles between is the other mistake that we commonly see on that. And then this one simple formula, okay? Any questions? Yeah.
So, if you want to, maximize the amount of stress you can apply, you want to do it normal to the slip.
Yeah, great question. What if you've got something like a hexagonal crystal? You remember from last class, we said hexagonal. They basically only slip along this basal plane, right? So if this thing is drawn in 3 dimensions, right? We essentially are only getting slip in that plane along the top. So if you were to apply a force straight up and down from it, all of its available slip systems are basically gone. It has some higher energy ones that go vertical, but if you apply it normal to that, then there's no component of shear that you're going to get. And so it won't slip. Instead, you'll get fracture. That crystal will fracture instead of slipping. But yeah, good question. Yeah. Under in the notes. I pass it?
Yeah, that one.
So, okay. This is the same thing as before. That's the same one that we just used. And the one that's below it, that's basically saying, okay, if you wanted to, that's to Rory, right? To Rory's question. If you wanted to maximize the stress that this could load, then you'd want to pick an angle that maximizes this. And you can actually show that. We've plotted it in Wolfram Alpha here, if this works, I think. So what I'm plotting here is that expression in 3D plot, right? So it's going to show you a heat map. And I'm plotting from the different angles that are possible, from 45 degrees to 90. And if Wolfram gets its act together, it basically shows you like where is the region that will give you the highest stress. And it's when both of those have an angle of 45 degrees. When both these right on this lambda axis and this phi axis are both at 45 degrees, that's when you maximize the stress that this thing could hold. So if you had a single crystal and you could choose the direction which you're going to load it on, if you chose the direction such that your normal plane and your slip direction they're going to be orthogonal to one another. They have to be, right? Because the plane is right here. The slip is happening in that plane, and it's got a normal into it. So they have to be 90-degree angles already. If you then load it straight up, so it's 45 degrees between the two of those, that's the highest strength that you'll get out of a single crystal. It's just mathematically what comes out of that equation. Okay? You don't need to know that for the test. So don't sweat it. If that's like going, don't worry about it. Okay. There are worked out examples of that. If you want to see more of this done in different ways, they're on YouTube. Okay? So let's talk more about, we're going to get towards something called Hall-Petch. But first we need to understand that slip in single crystals is different than slip in a polycrystalline material. In a polycrystalline material, well, take a single crystal material, things start sliding along that preferred slip system, and in a single crystal, it can just keep on sliding, right? But in a polycrystalline material, if you start slipping in one of these grains that satisfied your slip system, it's going to only slide till the end of that sort of grain boundary, and then it's going to hit another grain that's going to pin it in place, right? So you don't see the same mechanism at all. Instead, you can see grains sliding past one another along grain boundaries. You can see grains breaking, but it's a very different mechanism because these, on average, are all randomly oriented. So there's not like some direction that's more favorable than another. If your grains are randomly oriented, then all directions are equally favorable. In this picture, do you expect it to be the same strength in all directions? Maybe turn to your neighbor. Is it going to be the same strength in all directions in that microstructure or not? Okay, what do you think, Reagan? Is that the same strength or not? How come? Yeah. Like what if you tried loading it this way under tension versus this way? You can imagine that in the horizontal way, those grains are all kind of plates on top of each other. That looks a little bit like graphite or something, right? Those things can slide past each other more easily than the other way. If you try and load it the other way, these things are going to try and change, they're going to change their orientation to be in the field of the flow, of the plastic deformation. It's going to be harder, right? So these will definitely have different strengths, different elasticities in those different directions. So you can get polycrystalline materials that kind of look like single crystals in their behavior and that there's differences. And you can actually go through a process called texturing, where you make a polycrystalline material through a series of processing steps look more and more like a single crystalline material. This becomes really important for electronic properties. Like later in chapter 12, we'll learn about piezoelectrics. These are things that are just amazing. But if you had single crystals, they'd be the best, and those are too expensive to make. So instead, they make them out of polycrystals, and they align the grains. They make them really elongated, and then they line them up. And the way they do it's pretty cool. We'll get to it later. All right, there's another way that we can deform, not just like grains sliding past each other, but you can have twinning. We mentioned this earlier. First off, this cartoon is a terrible cartoon because it's wrong. What's wrong with this cartoon? What do we know about twin boundaries? What was the definition of a twin boundary? A twin boundary was a special type of grain boundary that preserved mirror symmetry on both sides of it. So whoever made this cartoon forgot that, because you've got your twin boundary right here. And if you look at it, this guy should have a reflection right there, right? But they haven't drawn it symmetrical, so there's a problem with this drawing, right? But the concept is right. If this was your initial position, all of those atoms at the same time can shift in the same direction, different magnitudes depending on which position they start at and how far they are from the twin boundary, but they all shift in the same direction. So this is a cooperative movement of a bunch of atoms. They all sort of shift together to produce this twin boundary. Why will that be any different than slip in a traditional sense? In a traditional sense, you have a single direction in your crystal that slip happens along, and it's a single row of atoms that change. Here, this isn't a single row of atoms that are moving, right? In that case, it's like a single bond is broken as the slip moves. Like if we go back up, it was like the inchworm moving through the material. We had like this, right? This extra half row atom, it steadily moves through the material by breaking and reforming bonds. That's not what's happening here in the twinning. In twinning, it's a whole bunch of atoms all shifting at the same time, right? Whole bunch of atoms at the same time. This one's correct. This one preserved the symmetry. This one's drawn correctly, right? So this is normal slip in a single crystal, and this would be twinning. Both of them can produce macroscopic deformation, but there's fundamentally different mechanisms. And you can get a pretty cool effect from it. Let's see if we can hear it. I brought my cheesy
In this demonstration,
speakers.
I'm going to illustrate deformation twinning using these two bars of freshly cast tin. So tin has a tetragonal crystal structure, which is in much lower symmetry than most metals.
Okay, tetragonal crystal structure. We've been talking about cubics like FCC. We said FCC and BCC have loads of slip systems. But tetragonal, now when you've got that one axis that's longer than the other two, you reduce your number of slip systems. Just like the hexagonal crystal that I showed you guys, where it's sort of like only along the basal plane. You get a kind of a similar phenomenon with tetragonal. So all of a sudden that crystal, tin, is no longer as likely to slip. Okay?
Which makes dislocation motion more difficult, and therefore favours deformation twinning. So I'm going to take one of these bars, and I'm going to heat it up using freshly boiled water.
Think when she's doing this, what that thermal energy is doing.
So I'm going to leave that there for just a little while, and in the meantime, I'm going to take this bar that's just at room temperature, and I'm going to bend it. And I'm going to do that quite close to the microphone, and you should be able to hear why in a second.
Okay, do you guys hear that? What on earth is happening here? It sounds like Rice Krispies going on in there when she bends that thing. You've bent plenty of coat hangers and other pieces of aluminum or whatever that's easy to bend, paper clips, and you never hear that. And it's not just that you're not listening closely enough, it's just that it's not happening. So why is it happening in tin? All right, be thinking about that. Meanwhile, okay. What about the one that's been in the hot water, though?
So now I'm going to take the one that's been heating up and do exactly the same thing to it.
Okay, so the exact same piece of metal at two different temperatures. One way it sort of makes a Rice Krispie noise, the other one it makes no noise. It looks kind of like you would expect, or sounds like you would expect. So turn to your neighbor, try and explain what on earth might be going on here. Okay, what do we think? Any thoughts? Why is it when you bend tin cold, nothing seems to happen? Or sorry, it makes a crickle noise, but when you heat it up, nothing seems to happen. Any ideas? First off, maybe there's two questions. One is, why is it different as a function of temperature? And then the other one is, what is that crackling noise? Those are the sort of the two questions we'd like to answer. So any ideas on either question? On either the role of temperature or what is causing the noise? Did your neighbor say anything insightful? Thomas, what do you think?
Is that 100% tin?
Yeah, it's pure tin, to my knowledge. Right? It's pure tin. So let me ask you this: if you what is sound in a material? What does a sound wave in a material actually look like? When sound, if like a mile away somebody takes a hammer and they smack a railroad, and you got your ear to that, and you hear it a mile away, right? Sound is traveling through solids much better than it is through air. Right? You couldn't hear a hammer strike a mile away, but you can hear it if someone hits the train track, right? So why? What's the difference there? What is sound in a solid? It's vibrations. It's atomic movements, right? Somebody smacked that thing with a hammer, and it caused a pressure wave, right? A local stress thing that constrained that lattice, and that wave of compressed atoms then travels through your material, and it comes out as noise that we hear, right? So if you move atoms, especially all at the same time, in all the same direction, we hear it. Well, that's exactly what's happening with twinning. In this cheesy cartoon, right? We had a bunch of positions that were the initial positions. These are the white ones. And then we twinned it, and they all shifted in the same direction. Sort of different magnitudes, but all the same direction. That is a sound wave, right? That manifests itself as a sound wave propagating through material. So when you take tin, which doesn't have a number of good slip systems, at room temperature anyways, and you start bending that thing, you're producing a bunch of twinning, which manifests itself as sound waves, because you've got big groups of atoms all shifting in the same direction. That's that little crackle and pop that you're hearing. It's not that anything's breaking in your material. It's just atoms moving all together, and your ear's picking it up. On the other hand, when you heat this thing up, when you heat it up, the slip systems that were less favorable at room temperature because they cost too much energy to make atoms slide past each other in that tetragonal system, all of a sudden you give it enough thermal energy that those become favorable over moving large numbers of atoms all at the same time. So this is important because this teaches us that when things deform in a material, there's not one way that a certain material will deform. It's not that it's either slip or twinning. It's that it depends. It depends on the environmental conditions like temperature. And so you can actually get deformation mechanism maps. I think we can find that. Deformation mechanism maps. So people have actually investigated this, and they produce these maps as a function of the type of stress, whether it's a shear stress or a normal stress, and as a function of temperature. And you can see all sorts of different regions, right? You get like plastic flow. Here you see power law creep, the same sort of creep that we talked about earlier in the semester. You've got diffusional flow. They'll often have things like slip versus twinning, but that's exactly what it's talking about. It's different mechanisms of materials deforming. It's going to be a function of the type of stress and the temperature primarily. Okay? All right, let's keep going. Generally speaking, when we've got a material, we have to compromise between strength and ductility. You can't have your cake and eat it too. And there's tricks we've come up with over the years, over the millennia, to try and get around this, but it's very hard to have a material that's both incredibly strong and hard and also ductile. They're diametrically opposed to each other. To have a material that is hard is to say that it's not going to deform, but a ductile material is one that does deform. So you can't really have both. It's going to be one at the expense of the other. Okay? So one way that we can control that relationship is with the grain size, right? Grain size. So smaller grains are actually stronger. That might seem a little bit counterintuitive, but smaller grains are stronger. And the reason why is because within a single grain, as atoms start to slide past each other, in a smaller grain, they're going to hit a grain boundary sooner. If they hit a grain boundary sooner, the odds of the two crystals next to each other being perfectly lined up, that slip can just keep on going because it's a nice perfect lineup, that's pretty low. It's probably going to be rotated off a little bit, so that slip's going to reach the grain boundary and have to change direction, or it might get pinned, or it might get dissolved, right? It might fix itself and heal itself and the dislocation goes away. All of that means that it's harder for the dislocation to move. And the rule that we learned last time, that restricting or hindering dislocation motion, that is a harder, stronger material. If that dislocation can't move easily, it's a harder, stronger material. So small grain boundaries help us do that. Okay? Therefore, you can see a plot like this. This plot is showing inverse grain size, right? So small grain size and large grain size is plotted up here. So this is inverse grain size. It's actually grain size to the negative 1/2 exponent, right? If you plot that against hardness or yield strength, then you'll see a linear relationship, right? It should have some constant slope that you could figure out from that material. That is the Hall-Petch law. This was like way back in the early days of material science. Somebody figured this out, and they said, holy smokes, when we make materials in different ways, and they've got different grain sizes, you can get this really big variation in your strength or your hardness, and this is just an empirical relationship. So you could fit it with a line, for example. Since it is a straight line, you could say that when you plot something like yield strength versus D, that's your grain size, to the negative 1/2 power, that it's a y equals mx plus b situation. The slope is going to be your constant k, and b is going to be the constant sigma naught. So these are just fitting parameters, right? These aren't like analytical first principles calculations. They're just fitting parameters, okay? And they obviously goes without saying they're going to depend on your material. Steel will have a different Hall-Petch relationship than aluminum. Will have a different one than anything else, right? All right, let's keep going. We already talked about solid solution strengthening. We talked about the impurity bubble that was bigger, right, than the surrounding bubbles. And so it locally was straining its lattice around it. So when a dislocation came zooming by, it said, hold on a minute. This region is locally compressed. So what if I point my region that's under tension towards that? It makes the energy go down for both things, both for the lattice and for the dislocation. So that dislocation, instead of keep on moving right past that impurity, it's going to park itself on the impurity and stay there. And in doing so, you made it harder for that dislocation to move because it's staying put. So you made a harder, stronger material. That's impurity or solid solution strengthening. Okay? And again, we use the term pinning. The dislocation got pinned at the impurity, excuse me. Okay? We've also got strain hardening via cold working. This is kind of an interesting phenomenon. So the blacksmith that's making whatever he's making, he's pounding on the metal. Each time he pounds on it, he's deforming the lattice, right? He's messing up the lattice. He's probably breaking bonds. He's certainly moving and introducing dislocations. And the more you do this, the more dislocations that are in there. We said that the average interaction for dislocations is repulsive. If things are perfectly anti-aligned, one's up and one down, they'll come and they'll annihilate. They'll feel an attraction. But most of the time, they're not perfectly lined up. They're sort of random directions, and so they're going to repel one another, right? So that repulsion makes it harder and harder for dislocations to move. Therefore, we made a harder, stronger material. So we call that strain hardening or cold working. And in principle, if you keep on, as a blacksmith, pounding on a piece of metal, it will eventually fracture, right? You keep on deforming it. It's going to keep on flattening, and then it will split in half. So there's a trade-off for blacksmiths on how often do you want to keep putting it back in the furnace versus the risk associated with it fracturing and breaking in half and then you starting over, right? The percent cold working, we can quantify this. We had this correct last time. It's actually the initial cross-sectional area minus the deformed area divided by initial. Normally when you think of like strain is... it's L final minus L initial divided by L initial. But here we're writing it the other way. We're saying A initial minus A final over A initial, right? The reason for this has to do with this notion. We know that the initial cross-sectional area times the initial length, if volume is conserved, then that should be equal to the final cross-sectional area times the final length, right? Volume's conserved. It can change its dimensions, but the overall volume should be roughly equal. So we can actually rearrange this with a little bit of math. We could say that the ratio of the initial area to the final area, the deformed area, that should be equal to the ratio of our initial length divided by our final length, which is really, we can rewrite this as delta L plus L naught. I'm going to call that L0, sorry. Keep the consistent terminology here. Divided by L naught. And that's just equal to delta L over L naught plus 1. And that's just equal to epsilon plus 1. So it's a pretty straightforward series of steps that we took. So if by the same exact math you wanted to figure out A naught over AF, AF over A naught, you end up with this extra term of epsilon over epsilon plus 1. In either case you want to do it, this quantifies the amount of cold working that's accomplished. If you know what the strain is in your material, say from a stress versus strain plot, then at any given point, we can quantify how much cold working has been accomplished. And it's typically reported as a percent. Is it 100% cold worked or 50, right? And it makes sense that the more cold worked something is, the stronger and the harder it gets. That's why you see these plots that do this. When we plot stress versus strain, you've got stress here, strain here. It has the linear region, and then it starts to do this, and it sort of increases. This increase in the plastic region, that's because it's continuing to deform. It's piling up dislocations. You're not taking it and putting it back in the furnace to heal those, so it's getting stronger and stronger and stronger until it fractures. Okay? All right. This brings us to three important terms in this chapter. Anytime you talk about deformation of materials in material science, there's three important terms. They are recovery, recrystallization, and grain growth. Okay? So the blacksmith has been pounding on whatever he's making, right, for a while. He's clearly messing up the lattice. He's introducing dislocations. He's actually going to be changing the grain size and the grain shape. So if we go back up to this picture from earlier, these grains are all sort of splatted out in one direction. This would be as a result of constantly applying stress in the same direction. So if you had a hammer forge, like he was using on the bronze pommel where it just pounded on it over and over, it might produce a grain structure like this after a while. Or more likely, this came from something that's hot rolled. If you've ever seen like how they make aluminum foil is like just absurdly thin. The way that they get there, it starts out as a big ingot of aluminum that's about a foot thick actually. Shocking. And what they do is they've got these rollers and they just basically make those a little bit closer together than your block of aluminum is. And they send it through. So it's going to slowly smash your material. And those grains get rolled out. The grains go from being nice round grains to being these pancake grains over time. They just keep on passing it through. They do it at a high temperature because if they didn't do it at a high temperature, then cold working would make this harder and harder and harder and probably eventually would fracture. But instead they do this whole process at a high temperature so that as you create dislocations, you're also giving it thermal energy for these things to annihilate again, making it ductile once again. Right? So that whole process is exactly what we're talking about in this section with recovery, recrystallization, and grain growth, right? Recovery means that you're going to heat something back up. We have a term for that. We call it annealing. When you anneal a material, that's just a heat treatment with the intention of removing stresses, dislocations, impurities in the material, okay? So your dislocations will find each other, they'll annihilate, your dislocation density will go down during the recovery. Therefore, your material should start to get a little bit softer, a little bit weaker during recovery. If you keep on heating it up, you will undergo recrystallization. So recrystallization means that your grains were so messed up from the cold working process that if you give it enough energy, you're not just going to move dislocations that will heal themselves. The whole lattice is going to recrystallize in a nice strain-free lattice, right? So strain-free grains will grow at the expense of your old deformed grains, right? They're going to grow with a much lower dislocation density, and they tend to be equiaxed, meaning circular, right? They're going to be spherical as opposed to sort of pancake-shaped, okay? And then if you keep on heating it up, you will get something called grain growth, where these grains continue to grow. We'll talk about that in a second. So here's, let's say the original material looks something like this. Let me zoom in. This was our original material. The grains were sort of spherical, roughly. You did cold working, maybe you did hot rolling over and over, or cold rolling, and you aligned the grains. So during recovery, the grain shape doesn't change, but your dislocations do change. So the dislocation from here to here, where recovery is happening, this is increasing temperature, the dislocation density would go down. But if you keep heating it up, these things are actually going to grow new crystals. See the black crystals growing there? That's the same phase of matter. It's just we drew them in a different color to illustrate that those are now strain-free compared to the stuff before. And it will just keep on growing until you get, they completely consume the old crystals and grow into them, okay? So again, here's our hot rolling process. Goes from nice equiax to really, very lined up. And if you do the heat treatments that cause recovery, recrystallization, and grain growth, then your final structure can still be just like your initial one. So this is a pretty powerful tool. By controlling deformation, which comes from the stresses you apply to it, and then the heat treatments, you can go from very, very different microstructures. You can achieve the deformation you want, and you can go back to your initial microstructure if that's what was desirable. Okay? When does this happen? Recrystallization typically happens somewhere between 1/3 and maybe 3/4 of the melting point. So it depends on the material, of course. Bonding in that material is going to dictate when it happens at. But you typically have to be at pretty high temperatures. Steel melts at something like, and it depends what type of steel, but around 1800 or so Celsius. So you have to get it pretty hot to get this, like it's glowing before this is really taking place, right? It's not just like you set it on a 100-degree hot plate for this to happen. Okay, grain growth. Grain growth is interesting. Grain growth happens because you're trying to reduce surface area. We know that surface area costs energy, right? It's full of broken bonds and not wisely used space. And so we want to reduce surface area. And if you've got a bunch of tiny little grains, then you have a ton of surface area. So instead of a bunch of tiny little grains, they grow. So this is a simulation. This is not a real experiment. This is some computer scientist did this. But what you're seeing here is a bunch of grains, and at any time I'm going to pause this, but like you've got small grains, like little tiny ones, and they might be next to a larger grain next to it. So keep an eye on those. Like take a look at this one. That's a really small grain in the middle next to these three big ones. How grain growth works is the small ones dissolve and the big ones gobble them up. This is like a sad allegory on life. Like the rich get richer and the small just get squashed, right? So it's sad, but let's watch it happen, right? You'll see the small ones disappear and the large ones getting bigger. And if you keep on giving this time and temperature, it's going to just keep on growing. You're going to keep on reducing the grain density, or the grain boundary density, by having big grains grow and grow and grow. Now remember, Hall-Petch tells us that this is now a weaker material than we started with. That is definitely not the strong material that we started with. So there's a trade-off to be had in doing this. You might change your grain size in a sort of shape that you're interested in, but it might come at the expense of strength, right, during this process. Okay? Why do you think, do I have it written here? Yeah, I don't have it written here. So maybe turn to your neighbor and why on earth do you think it's the case that small grains dissolve and big ones absorb them? Why is it not the other way around? Like, what's driving that? Can you think of a physics principle that might be driving that? So turn to your neighbor and discuss for a second. Okay, what do we think? The small grains definitely dissolve away, and the big ones absorb them. But what's the mechanism? What's the physics why that should happen? We know that there's a difference in energy, but like, what's the mechanism by which it happens? Any ideas? Any thoughts at all? So it has to do with, yeah, Josh?
I was just going to say, so at the grain boundaries, you've got strain, right? Because they're not, on the edges of the grain boundaries, they're not, the bonds aren't kind of ideally connected.
Yep.
And so, in order to lower the energy, basically, they'll try to bring those bonds in balance, and so they'll kind of create bigger grains with less balance.
Yeah, so if this is like a grain boundary that is a very large grain, and so that grain boundary has what we call a very large radius of curvature, compare that with this one, right? These atoms with the small radius of curvature from a small grain, those are locally more strained along that grain boundary than these ones are. So these guys over here are just less happy than the ones over here. So if they have their option to dissolve, like if they can leave that grain boundary, this atom gets up and it travels over here and then redeposits over there on the surface of this thing, it will do so. So it literally can be calculated, the mechanism of this, assuming solubility. That literally the solubility of these guys, because of the strain, which is exactly what you mentioned, is higher solubility, and these have a lower solubility, you're going to see a net migration to the surfaces of the large grains. Okay? Which is pretty rad. Okay? It's not pretty rad when it ruins your ice cream, which it does. If you ever notice, like ice cream, you take it out of the freezer, you eat a little bit, and then you're like, I wasn't quite done, and you go take it out again, grab like another spoonful, and you keep on doing this over a couple weeks. What does that ice cream look like after a couple weeks? Anybody notice this before? If you're like, ice cream lasts a couple weeks? The more times that you take it out of the freezer, when you take it out of the freezer, you're essentially doing what? The melting point is not that high, and locally in that room, it's certainly above the melting point of ice cream. So you are doing grain growth and recrystallization, depending on how much strain is in that, right? So these things are going to grow and grow. What is ice cream made of? All it is water and cream and sugar, right? So actually what happens is that if you give it enough thermal energy, these things start to separate. Just like milk, if you let it sit for long enough, it will actually phase separate. You ever seen this? Where like the cream separates from the other stuff, and you leave that long enough, it will separate also. So ice cream, that happens at a pretty rapid scale because what they put into these things. So the water will separate from the cream and the sugar, and so you get these big, really big exaggerated ice crystals growing in it. Anybody had ice cream with like the big ice crystals in it? It's the worst. That's grain growth, right? We have a name for it. We call this grain growth process Ostwald ripening. Ostwald ripening is just the big grain swallowing up the little ones. And we can actually model it. The reason I bring it up for this class is that this process can be modeled. It obeys a kinetic equation, right? So the grain growth at any given time, so the grain size at any given time, that's going to be d, raised to the n, that's going to be a constant, will be equal to d naught, our initial grain size, raised to the n, that's going to equal kt, right? So if you know what these constants are, k and n, which are not the same constants k and n as we've used for anything else. Sorry, material science is a study of everything. We run out of variables for these things. But k and n are constants for grain growth. And if you know those, and I were to give you an initial grain size, and I say, how big will it be after 5 hours? You could tell me those. So obviously k and n are time independent, but they will definitely depend on temperature, right? If you hold something for 5 hours at room temperature, the grains won't grow very much. But if you heat that thing up at an elevated temperature, it could grow a bunch. So K and N depend on temperature. And if you understand what they are in a material, like let's say a simulation expert generated those values from matching experimental data to simulated data, all of a sudden now you can understand what your heat treatment will do in terms of growing your grain size, which is a powerful thing to know since it relates to strength and everything else. Okay. So we talked about metals and deformation mechanisms in metals. There's twinning, there's slip in single crystal versus polycrystal materials. There's the recovery, recrystallization, all that. But there's other class of materials than metals, right? So there's ceramics, and slip in ceramics is really, really hard. And the reason why has to do with the fact that they've got negative and positively charged ions. So imagine what happens if I try to slide this past each other, right? Let's say I pick this as my slip system. That's my highest planar density in the highest linear density direction. So I'm like, oh great, I'll just slide these things past each other. The problem is, halfway through when it slides past each other, you have to have a negative next to a negative, positive next to a positive, right? That's a huge electrostatic repulsion on all these points. So it generates so much electrostatic repulsion as you slide them past each other that it says, screw it, I'm just going to fracture. This causes me so much strain in the lattice, so much energy penalty. It's cheaper for me to fracture and create two new surfaces, which also costs energy, but that's less energy than bringing these things next to each other, right? So even though you might expect slip to happen in these because of like the symmetry of these things and really high planar density, high linear density directions, it doesn't happen because electrostatic repulsion, okay? So if they can't slip, then you could say, well, maybe they're going to twin, and twinning is a little more likely, but it's also pretty high penalty. So with the absence of a good mechanism of deformation, ceramics just fracture. This is the reason why they have essentially no plastic deformation, is they don't have a low energy method to achieve it. If you heat a ceramic up close to its melting temperature, then it will deform, right? These deformation maps that I showed you earlier, if you look even at ceramic materials, at high temperatures, they will exhibit some plastic flow, but it's typically like really, really, really high temperatures. And it might not be slip dislocation, it might actually be flow. So what is flow? Flow is something like in glasses, right? A glass is a ceramic material, and if you heat it up enough, we know that we can deform it, right? But the way that it deforms is via flow, plastic flow. It's big swaths of atoms all sliding past each other. It's not some twin boundary where they're all moving the same direction. It's not slip where it's individual atom planes moving. It's large numbers of atoms flowing past one another. So to characterize flow, we need to understand viscosity better. Viscosity means you've got a material. That's going to be shown in this section. So this is a material that you're testing. You take a moving plate on the top of that material, and you have a stationary plate on the bottom. So you're basically dragging along the top surface of it, right? What you'll see is that there's a gradient in the velocity of your material. If your plate's moving at a u velocity, then you're going to see this sort of gradient in your velocity. From that gradient, you calculate viscosity. Okay? The actual equation looks like this. So eta, that's our viscosity. Eta, that's the Greek letter eta, ETA. is equal to tau, that's the shear stress that you're applying, divided by the gradient, or the gradient in your velocity in that vertical direction. Okay? So F over A divided by dV dy in that denominator. Therefore, because of this, this should have the units of Pascal seconds, right? So just like stress has the units of pascals, or usually megapascals, right? Same thing, just a million of them. This has pascals but times seconds. And we have an important temperature, which we mentioned before. We have the glassy transition temperature. That is defined at the point when your viscosity equals 10 to the 12 Pascal seconds. And really, that's sort of the onset. But below that glassy transition temperature, it really looks like a ceramic. But if you go above that temperature, all of a sudden it becomes sort of rubbery, and eventually it might even flow. Okay? We have a pretty cool expression. It's an empirical relationship, and it helps us calculate the viscosity at any temperature. It's right here. So it's this eta is equal to eta naught. That's going to be multiplied by the exponential of what's inside of here, negative 17.4, and the difference between the temperature you're at and your glassy transition temperature, right? You can do this in Celsius or Kelvin. Since it's a difference in temperature, you'll get the same number. Technically, each material, you should determine what these values are. The negative 17.4 and the 51.6, they are material dependent. So these are just general values. These are sort of estimating values. Okay? Let's talk about polymers for a minute. As you deform polymers, they undergo a series of steps. This might be your polymer when you start out. In that material, you've got clearly a crystalline region. That's this sort of square blocked out region. That would be crystalline. That's the chains folding past each other in a way that's crystalline. But then you've got the sort of messed up amorphous regions between those. So as you pull on this polymer, the first thing that's going to happen for it to deform is it's just going to stretch out these amorphous regions. They were already not well bound together because they weren't crystalline. So they're just going to stretch out. And entanglement will keep them from stretching out perfectly, but they will start to stretch out. The next thing that will happen is these crystals, which had been oriented this way, are going to shift their orientation. It's going to stay crystalline, but it changes its orientation. Rather than lines like this, it switches to vertical lines, right? If you keep on stretching a polymer, those will start to break up. Now you've got portions of your crystalline region broken up, and eventually, if you keep on stretching it, the final stage looks something like this, where you've got your chains very heavily aligned in one direction. So the question is, what should happen to strength when you do that, right? What happens to the strength when you go from this all the way to this point? What should strength do? In which direction? In this direction, you should see a massive increase in the strength. The reason why is because you've run out of polymer strands you can sort of straighten. And now, because some of them are already straightened out, you have to start breaking covalent bonds to stretch it further. You have to start fracturing your material, right? That costs much more energy. So the strength going through this process goes up and up and up and up. So you can make a much stronger polymer by deforming it in one direction. And the way that they deform polymers in one direction is by drawing. We showed this with the nylon 6/6 video. Remember the nylon 6/6? They grabbed that interface, they pulled it up, and they were like winding it around the rod. As they were doing that, like all the polymers were sort of starting to line up. And if you do that over and over and you keep on drawing it, or you draw it down to smaller and smaller diameter, you can really make high-strength polymer fibers. So ropes, right? This wouldn't be a good climbing rope, because this thing, you've generated a lot of strength at the expense of all of its ductility. So a climbing rope, you'd actually want something neither end, remember. You'd want strength, so maybe part the way here, but you want some of this amorphous region to be elastic, right? You want to have some ability for this thing to stretch without breaking. And we're out of time, so we'll do the final bit here next class, and then we'll dive into diffusion next class.